Well, my topic is crustal measurements for signal integrity applications. First, we have our theme. As signal speed increases, crosstalk has become a major contributor to signal integrity issues. The challenges are compounded by the need of equipment manufacturers to maintain or even increase port density. Here's a video.
You are watching a series of videos that cover signal integrity measurements using the ZVA True Differential Network Analyzer from Rohde & Schwarz. In this video, I'm going to show how to set up and calibrate a network analyzer with 4 ports so that it's ready to make true differential measurements on a signal integrity board such as a differential line like this. To perform the calibration, I'm going to use a 4-port AutoCal unit, which is connected to the network analyzer with a USB port, and it's also connected to the network analyzer with 4 RF cables. The only thing I need to do to enable the calibration is to set the frequency range. In this case, I will start with 50 megahertz, and I will stop with 8 gigahertz, and I will use a frequency step size of 50 megahertz. This provides me with a harmonic grid, which the time domain transform will take advantage of later. The next thing I want to change is the IF bandwidth. In particular, I want to enable dynamic bandwidth reduction, which improves the dynamic range of a microwave network analyzer. Once these 2 settings have been made, I am ready to calibrate. I select Cal, Start Cal, and then if an AutoCal is present, this calibration unit button will be active. If I select this, the network analyzer will communicate with the AutoCal and automatically determine the port mapping between the network analyzer ports and the AutoCal. So for me, at this point, all I need to do is press the start button and the calibration process will start. As you can see, it's a fairly quick process and there's no interaction from the user during the calibration. It's already complete. I can close the calibration window, and the next thing I need to do is save this calibration for future use. To do this, I select Cal, then Cal Manager, and I can copy this current calibration from the channel to the calibration pool where it can be used in the future. Before I do that, I normally check the different parameters down here as a summary window where I can audit the date and time that the calibration was performed, the frequency range over which the calibration was done, and which ports were calibrated. In this case, I see that everything is the way I'd like it, so I will select a calibration pool entry, which I called Signal Integrity Cal, and I will replace it with this most current calibration. And that's it. At this point, I have a 4-port network analyzer fully calibrated and ready to make signal integrity measurements even with a true differential signal. That's
At the same time, many engineers struggle to determine what part of a signal integrity problem is due to crosstalk and what is due to jitter. In this webinar, the concept of crosstalk and various types of crosstalk will be introduced and explained. Common available tools to evaluate crosstalk will also be reviewed.
First of all, you'd have to set this up with 2 pseudorandom bit streams and do the same thing with the voltages, make them conversely. V low has a value and then 0 here, just like you saw in the other example. And I could use the same timing variables, and I've set this to run at 1,000 times T-bit, which is, if you recall, 1 over our data rate, and in this case it's 5 gigabits per second. And then you could use an iProbe or our V positive and V negative to write an equation. And for the iProbe, I don't want to check this box because in this case I want my transient output. Let me show you the results of this simulation. Here in the status window you can see that it takes about 25 minutes. And here in the data display you can see the results for transient. We have a similar iProbe density plot, and then here's the equation using the front panel eye diagram. And here you can see a comparison of the transient results to the channel simulation results. And while these eye diagrams or density plots are similar, there's a big difference in the amount of simulation time and also the settings that are allowed with these transmitters and receivers. In this case, we have the 8B, 10B encoding available. So again, if it's linear, time invariant, and it's large and hierarchical, then you want to use the channel simulator, because every time you make an adjustment, it's not going to be another 20, 30, 40 minutes to run the analysis, only a minute. And now let's move on to the final example, which shows how to tune taps with channel simulation. Here's a simple design named tuning, and the transmitter shows two post-cursor taps, T0 and T1, and those are set up here with variables, so we can tune these. I'm going to use the tuning icon, and
There's another video.
So before I demo the channel simulator specifically, I wanted to show you one of the unique things about advanced design system that traditional SPICE-like simulators just don't have. It's something that's very important in the multi-gigabit regime. When the bit period is shorter than the flight time of the wires, the ends of the wires aren't at the same voltage anymore. They behave like transmission lines, and you have to model these distributed effects, microwave effects if you like, at the level of the physical layout or the artwork. So besides traditional lumped elements with terminals on voltage nodes like you'd find in regular SPICE, ADS models transmission lines in various levels of detail. So here we have lumped elements and so-called lookalike components. Underlying the lookalike components are the actual artwork that you can manipulate and experiment with in ADS layout. You can even visualize this in 3D.
That's all. Thanks for watching.